Hello, I'm Mark Oliver. I'm the VP of Marketing at Efinix. I'm going to be talking to you today about the Efinix TinyML platform. But before we get into that, since I'm sure most of you have probably not heard anything about Efinix, it probably makes sense to spend just a couple of minutes and talk about who we are. So we're an FPGA company. We redesigned from the ground up what it means to be an FPGA. And we've ended up with an FPGA platform that is lower cost, that is lower power, uses a small footprint, and we're dedicated to making those FPGA solutions available to mainstream high-volume applications. How we did that and what the redesign of the FPGA fabric looks like can be a topic for another discussion. So let's get back into machine learning, AI. Let's talk about some of the challenges that people see out there. So for a start, the complexity of models is increasing. I think we would all agree with that. Also, the rate of innovation, the rate of the models evolving is increasing. And all of that means that custom silicon is having a really hard time keeping up. So the cost of each progressive custom silicon node is getting more and more expensive. The risks and the development time are going out. So really, custom silicon is increasingly becoming not a viable option for AI challenges, and particularly at the edge. The edge is, after all, where most of the data lives, and it's where AI and machine learning really should be so they can be close to the data. That means that power is at a premium, obviously, and inevitably compute power is not going to be there. So traditionally, the way people have solved that kind of problem is with AI accelerators. When we've looked around at accelerators, we find that most of them are not granular enough, so they tend to incorporate large pieces of a model, and that means they don't scale too well. They're also too high power, and most of them, by definition, are proprietary, so you have to learn how to use them. All of those challenges are things that we at Efinix solved when we tried to come up with a new and revolutionary concept for an FPGA. So the question then becomes, how do we make these FPGAs that solve those issues available in an intuitive way to the AI and ML community? So one of the ways that we found resonates with our customers is by giving people the ability to do hardware-software partitioning. So we've incorporated a RISC-V. It happens to be one of the highest performance and most rich RISC-Vs that you can get out there right now. People can use that to create applications and algorithms in software on the RISC-V. And then once they've perfected that at software speed, iterating the way people do in software, they can then take a look at the performance that they're getting out of that algorithm and can progressively start to accelerate it in the FPGA fabric. That gives people a fast time to market, and it means that they can exploit the parallelism that's inherent in FPGA architectures. So let's take a look at the RISC-V, just to set us up for the rest of the conversation here. Our RISC-V, we've actually made it fully user configurable, and it's user configurable through a GUI so that the user doesn't have to know all of the VHDL behind the RISC-V. They can simply configure it the way they want it. Bullet 3 there is an interesting one. It says custom instruction capable. So we should probably talk about that for just a moment. It turns out that the RISC-V architecture doesn't have all of its instructions defined. There are a few that are left open for the designer to define and implement him or herself. So what does that mean? That means that you can design your own custom ALU, in our case, out in the FPGA fabric, which is why RISC-Vs work so particularly well inside FPGAs. But you can define that custom ALU to do whatever you want when called upon by that custom instruction. Now, fundamentally, at least, that custom instruction has the same architecture as the rest of the instructions. So you end up with 2 source registers and 1 destination register. Each of the source registers is 4 bytes wide, so you have 8 bytes of data to work with and 4 bytes of result that you can pass back to the RISC-V. But it gets better than that. The custom ALU that you've created, your very own ALU, is actually sitting out in the FPGA. it has access to the FPGA, and it can pull data, if it wants, from the FPGA. So you're not necessarily limited to that 8 bytes of data that you pass into it. You can make your ALU arbitrarily complex. You can give it access to data that you've put out in the FPGA previously. You can give it access to data that's coming in from sensors, for example. And then you can call that ALU with your custom instruction. So this becomes a really powerful way of exploiting the RISC-V and allowing that to control the, the, the movement of data and the compute in your system. So what we did, we have taken the architecture of the custom instruction and we've adapted it for AI and machine learning. So we've leveraged a lot of the excellent work that's going on with the TensorFlow Lite open source community. We've made sure that the TensorFlow Lite Micro C library runs, and those models will run on our RISC-V. And we can then accelerate the fundamental elements inside that TensorFlow Lite model with custom instructions in what we're calling the TinyML accelerator library. So how does that work? Well, we can take the TensorFlow Lite model and we can run it on the RISC-V in software, just as you would in any other microcontroller, and it'll run there totally happily. You'll probably find that you're not getting the kind of performance that you want out of it. So we're able to implement the fundamental models, the fundamental building blocks inside that TensorFlow Lite model, implement them in custom instructions, and get a huge acceleration on the way that that model runs on our RISC-V. Now, you might think that we didn't have the right approach to some of that, or you wanted to accelerate some other aspect of your SoC. So by all means, go ahead and create your own custom instructions, your own accelerations of that model, anything else you want to do. You're free to innovate and create accelerations on top of that RISC-V. Once you've got that the way you want it, you're going to want to deploy that model. So we're also making that totally compatible with the other quantum acceleration frameworks that we have. And I haven't mentioned that yet in this talk, but if you want to figure out what quantum acceleration is, go to the website, look at things like the Edge Vision SoC, and you'll see that you can take these fundamental elements that you've now accelerated on the RISC-V. You can bury them inside an SoC framework that we give you for free, and you can accelerate that with sockets of acceleration that we've defined for you, and we've given you examples on how to use them. So look that up. It means that you can turn what you've generated on this RISC-V into a product and deploy it extremely quickly. So what does that give us? Well, first of all, there's no third-party network compilers here. What we're doing is we're leveraging the same tools, the same open source infrastructure that I'm sure you're all familiar with working in this industry. We're not forcing you to learn anything else. The only tiny bit that you do have to learn is how to code a custom instruction, and it's trivial. It's a very, very small amount of VHDL, and we'll give you templates to help you do that. It is fine-grained, which is one of the things that we wanted to achieve. I mean, we're accelerating machine instructions. It doesn't get much more fine-grained than that. And it readily adapts to just about any new network architecture that you're going to come up with. If you can express your new network architecture or your new model in software, and you know you can, then you can take that software and you can accelerate it at a custom instruction level. It retains 90% of that model is in software still, and it's running on the RISC-V in C or some other language. So you're doing that software, hardware partitioning, which gives you an extremely fast time to market. And of course, when you're done, you still get the system acceleration that we're talking about. So let's take a look at what that means in practice. So as an example here, we took a model, arbitrary model. This one happens to be YOLO Pico, but it really doesn't matter. We ran that on the RISC-V in software, and then we took the most simple custom instruction that we come up with, those 2 registers in, 1 register out, and we accelerated the convolution, which is where most of that model spends its time. And we found that just the convolution part of that model was increased by a factor of 4x, which is not bad already, but we figured we could do better. If you remember, I said that the custom instruction has access to the FPGA. So we came up with a custom instruction that used data that we'd pre-placed inside the FPGA and ran that. Surprise, surprise, we ended up with a custom instruction that has a 59x improvement on the convolution portion of that model. I also said that the custom instruction can be arbitrarily complex. So we went to town on this custom instruction, and we figured that we'd increase its size slightly. And with very little extra work, we came up with a large convolution instruction that gives us 213x performance on the convolution. So impressive, but kind of taken out of context. So let's have a look at a real world example here, and I'll show you the way this works in a design flow environment. So here we have a media pipe face mesh. If you were at the face-to-face version of this show last week, you'd have seen us demonstrating this on our Titanium TI-60 dev kit. So this is what you would have seen at the show. It's running at 300 megahertz on that Titanium TI-60. And we did a profile of where the RISC-V was spending most of its time, and surprise, surprise, the vast majority of it is in convolutions. So we said, well, what would happen if we started putting together custom instructions to accelerate progressively these Pareto items of where it's spending its time? So we came up with that simple 2-register in, 1-register out convolution accelerated instruction. We stuck that in there, ran it on the RISC-V. Surprise, surprise, we're seeing, what is that, about a 4 or 5x improvement on the time spent doing those two convolutions, which is what we would expect from that simple instruction. So already a pretty decent improvement on that latency, but why stop there? If we go down the Pareto items, we can see the next one is the add. So let's stick in an add instruction. You see the resources that we're using inside the TI-60 go up just a little bit, but not too significantly. These custom instructions are very small pieces of code. And you'll see as we go down, we'll add the maximum in next, and then the mult. And we're getting a kind of a diminishing returns here simply because the RISC-V is spending less of its time doing those operations. So exactly what you would expect. So we've got a fairly good improvement already, but we also said that that ALU that you've created, your very own ALU, can be arbitrarily complex. So we pulled the original conv out, and we put one of those slightly more complex ones in just to see what would happen. And again, we're starting now a whole different slope on that graph just by putting a slightly more complex convolution acceleration instruction in there. You'll also see, if you looked at the resources there, that they jumped up fairly significantly because that custom instruction is a more complex instruction, and so it took more resources inside the FPGA. So our boys and girls in the lab decided it would be fun if we put the TI-60 aside for a moment and we powered up our TI-180. Shameless plug for the 180. It's the latest version of the Titanium family. We released it about 3 weeks ago. It's 3 times the size. It has a really good memory interface on it, and it's a really, really good device for things like AI, ML, and for edge compute. So that gave us all of the space that we needed, all of the scratch pad to put in some of the 2nd and 3rd generation parameterizable custom instructions that we're working on. You see what happens. So using that larger device, it crushes this latency down almost so that you can't see it on the graph here. Again, just using 4 or 5 custom instructions and the rest of the code running on the RISC-V on this TI-180. Very impressive. So let's put the TI-180 aside again. Let's pick back up on that TI-60. You can also do a couple of things, of course. What you're doing here is you're making the processor more effective, more efficient on the algorithm that you're trying to run. But what happens if you don't need all of that latency reduction? Well, what you can do is you can turn the clock down on the FPGA So obviously your latency goes back up again because the FPGA is now running slower. But look what happens to the power there. It goes from a normalized value of 1 down to about, what is that, 0.15 or so. So if you're an edge application where you don't need super fast latency, but you do need low power, using custom instructions gets you to do that trade-off in exactly that way. You can be accelerating the processor to customize it for the application that you're running, slow the clock down, and save a ton of power. So, in summary, what we're looking at here is a future-proof solution. And I say that because, as I said earlier, if you can express your algorithm in software, and you can, and you probably always will be able to, then we can accelerate that software at a machine instruction level or at a level of granularity that makes sense for the FPGA. FPGAs absorb new architectures. That's what they do. That's why they were designed. They love it. So you can throw new architectures at your FPGA. You can do that hardware-software partitioning, but rest assured that the model that you come up with is going to fit into that FPGA. And if it ends up being a transformer or the like that has all manner of internal connectivity, FPGAs can do that. So you're pretty much future-proofed. And remember, of course, that you are dealing most of the time still in software. So you're doing the hardware-software trade-off, and that means you can innovate rapidly. You can do it at software speed. And when you're finished innovating, you can accelerate that in the hardware to get the performance that you want out of the system. So what is Efinix delivering as part of this? We wanted to make sure that as people adopted this technology, adopted the Efinix FPGAs, they had a good end-to-end experience. So we've come up with a whole bunch of Jupyter notebooks that do tutorials that will walk you through how to do some of the hello world kind of applications and the examples that we're putting in this bundle. It'll teach you how to take untrained models, train them, and quantize them using Colab. So a real on-ramp, if you like, onto to how you do some of this stuff. We've also made sure that the TensorFlow Lite libraries work on our RISC-V so that once you come up with a trained model with your Jupyter notebooks and Colab, you can run that on our RISC-V seamlessly. And then the cool stuff, we have the TensorFlow, the Efinix TinyML library, so all of those custom instructions. That library will expand as the TensorFlow Lite definitions expand, and they are getting larger. We've also given you the SoC framework so that you can take what you've done, what you've trained, what you've optimized, and turn it into a deployable product very easily. And we've given you all of the custom examples, the hello worlds, the complete design flow end-to-end in an expanding model zoo, and our folks are having a blast expanding that zoo as fast as they can. So all of this is part of the TinyML platform that we're delivering. Where can you get it? Well, you can get it on our GitHub. So we are giving this to the community. If you go to the GitHub, take a look. You can see the screenshot of it there, but you're going to find examples. You're going to see the accelerator libraries I've talked about. You're going to see models. You're going to see trained and untrained models. You're going to see Efinix projects. Efinix is the FPGA toolset. So we're going to give you projects that teach you how to import some of this stuff in, how to compile it for an FPGA. And if you can't be bothered to do any of that, we're going to give you the ready-to-run compiled examples so that you can stick them onto your FPGA development kit. You can run them, and you can see what the end result's going to look like. So I think we got a winning combination here. I think we're combining the efficiency of Efinix FPGAs, and they are inherently more efficient because of the way they're designed. We're giving you the design efficiency of developing in software on our highly effective RISC-V and doing that trade-off between hardware and software, accelerating the software at hardware speed and giving you the ability to very rapidly evolve your design to something that you can deploy. And we're making that available to the huge community of open source developers off the GitHub. Final thing, another shameless plug for our Titanium TI-180. I said that we released that about 3 weeks ago, something like that. throughout the summer and into the fall, why don't you go pick up a Titanium TI-180 dev kit, go download this platform, put the two together, test drive it, see what you come up with. We'd love to hear the results. Everything that we do internally, quite frankly, astonishes us with some of the results that we're getting. We would love to see you guys kick the tires, take it for a test drive, and let us know what you think. So with that, I think I am out of time. I'm hoping that my email address will be part of this speech talk somewhere. So if you've got questions, if you want to give me feedback, look me up, shoot me an email, and we'll take it offline. Many thanks.